Hello, my name is Ryan Zbikowski. I'm a PhD candidate here at CSRC, and the research I am sharing is titled Natural Orbitals for the Nuclear Many-Body Problem. Before I get started, quick shout out to the CSRC staff, my advisor, Dr. Kelvin Johnson, and the Department of Energy for making this research possible. All right, let's dive on in. All right, state-of-the-art low-energy nuclear science is supported by the success of fully quantum mechanical calculations of nuclear wave functions. My overarching goal with this work is to reduce the computational costs associated with large-scale shell model calculations. Turning our attention to the first bullet point, given a Hamiltonian operator which includes an interparticle interaction, we solve for the energies and eigenvectors of the non-relativistic many-body Schrodinger equation cast as a matrix eigenvalue problem. The nuclear many-body problem is conceptualized at an infinite-dimensional Hilbert space, but must be truncated to a finite one. As a consequence, the choice of single-particle states used to construct the basis and many-body truncation both play an important role in the convergence of solutions within this truncated space. Typically, one is only interested in a small set of low-lying eigenstates of the Hamiltonian, which can exceed dimensions of 10 billion or more in the largest size problems. And these matrices are often very sparse. 1 in a million matrix elements may be non-zero. All right, let's jump in and how we construct the many-body wave function using our method. Configuration interaction is a popular method of constructing the basis for the nuclear many-body wave function, and the configuration interaction calculations expand the many-body wave function in an orthonormal basis containing all the useful information about the behaviors of the nuclear wave function. We can also apply the approach as seen in bullet point 2 of constructing the Hamiltonian matrix elements to other operators corresponding to physical observables of interest. The advantage of the method of the configuration interaction method are many, but I'll highlight a few here since I have your attention. First off, configuration interaction allows for the arbitrary choice of single particle basis, very important, though it is traditionally the case that one uses harmonic oscillator states for their computational conveniences, which I won't go into here. Also, configuration interaction allows for the arbitrary form of the two-body interaction, i.e. no restriction on locality or momentum dependence. All right, let's talk about natural orbitals. Natural orbitals are a unique set of states guided by the wave function itself for the improvement of its own description, and they originate from atomic physics and quantum chemistry. Natural orbitals have empirically shown to reduce the dependency on the initial basis parameters, such as the oscillator free energy, and they accelerate the convergence of long-range observables by improving the tail of the many-body wave function better than harmonic oscillator states. For the construction of natural orbitals, we diagonalize the one-body density matrix of the ground state, which contains information about the correlations in the many-body wave function, though in principle one isn't necessarily restricted to the ground state. You could use an excited state and use those one-body density matrices as well. Lastly, it is important to note that the definition of density matrix doesn't actually depend on the choice of basis for the single particle space. All right, now let's talk about some results. I have two cases to present here, sodium 22 and sodium 23. The left panel is a shows the ground state energies of sodium 22 at different harmonic oscillator frequencies. I want to draw your attention to the colored squares here, which highlight the Nmax truncation. I'm not going to go into the details of Nmax truncations, but you can intuit it as the lower the Nmax, the smaller the dimension of the basis that we use to get our results. For both Nmax 2 and Nmax 4 truncations, we find that using a natural orbital single particle basis does seem to lower the energies seen in the plot, though the majority of the impact seems to be when the frequency of the underlying basis is far away from the variational minima shown at 22.5 MeV. The right panel shows a more profound effect of natural orbitals on the RMS charge radius of the ground state of sodium 23 as calculated in, again, two different size truncations. The RMS charge radius is more sensitive to long-range asymptotics of the single particle wave functions used to construct the basis. Not only do natural orbitals accelerate the convergence of the observable, but we can also kind of quantify about how much our results improve because of using the change in single particle basis. More simply put, our Nmax 2 calculations in the harmonic oscillator, or sorry, the natural orbital basis were comparable to our Nmax 4 calculations in the much larger space using harmonic oscillator single particle states. So our 8 million dimension calculation produced radiative values, which was comparable to the 1 billion dimension calculation, which is pretty fascinating and pretty awesome to see happen. So I'll have more information about natural orbitals at my poster. Hope to see you all there. Hope you learned something.